So welcome everyone to our very first TopOpt-Talk. My name is Ngoc. I'm a PhD student in the group of Michael Stengel at the University of Erlangen in Germany, and we're in the business of structural optimization. And today I'm here with my colleague Fabian.
Hello, I'm Fabian Weim. I'm from the same group in Erlangen. I'm a senior scientist. We thought after the WCMO that we start with a TopOpt-Talk, where we want to talk about topics in the field of structural optimization, topology optimization, SIMP method, which are, well, in our eyes, probably worth to talk about.
And our target audience is everyone that is interested in the area of structural optimization, and we assume some basic understanding for the matter, but it also means that our talk is meant for not only PhD students, but also advanced researchers and master students who have worked or been studying this field for a bit.
Yeah. And originally we wanted to talk about Ngoc's presentation from the WCMO, which was about two-scale optimization and how far this two-scale optimization makes sense. But then we found that we shall probably start a little bit earlier, and we simply want to talk about grayness. And it's not even sure if we can cover everything about what can be talked about grayness in the first podcast, but well, we just wanted to give it a try. So when we talk about grayness, the question is, what does it mean when we have intermediate materials? And this is all what is the basic idea of the SIMP method. It's all about the grayness, and it's all easy and all not that easy, depending on how close one wants to have a look at it. And I first want to start with the very first paper in our field from Benzo and Kikuchi from '88. This is the very first paper of topology optimization in our field, which means how can we make holes. And what I want to focus here is what people did, what Martin Benzo and Nobuo Kikuchi did then. They had cells partly filled, parameterized by simple parameter. And what they then did, they changed the field. And what they observed is, how do the material coefficients here change when they change the density? And in the very first papers, this was a very difficult approach. They had a two-scale approach, which is well still used and still reinvented and so on. But the point is, when we have a single cell and we have it either full or empty or intermediate. When we have it intermediate, we have a parameter for structure inside the cell, and from this parameter, which tells us the density is how far is the cell filled, we have resulting material properties.
So how do you get from the cell parameters or such a geometry to these resulting material properties?
When we have a periodic cell, for any periodic cell, we know what is the density, how much for any periodic cell we can, by mathematical homogenization, determine what material coefficients do we have, and we also know how far is, to which extent is the cell filled, which is the density. And when we can parameterize the cell, that we can change the density, we can observe what are the resulting material coefficients. And here, by mathematical homogenization, which is complicated, expensive, and so in the next paper, very important paper where, so to say, the SIMP method was first introduced. This is from Martin Wenzel from 1989. He observed, well, when I do the optimization, in the end, I anyway only have a black and white solution. So I do not really care what I have in between. So again, this is what we had in the previous paper. We have this curve as a function of the material coefficients as a function of our density. And what he then did here, he said, well, when this is my parameter, the density mu, I approximate this curve as a power law. And with this power law, I scale the full material. And this is actually a very coarse approximation of what he had, of what we would get with a homogenization. And there are better curves than power law, but this is simply what Martin Wenzel did there.
So does it this type of interpolation, does it really work for all types of materials, or
no, only for isotropic material? Or no, to say
it would also work with orthotropic material, I would say. You just need more interpolation schemes.
Or it depends. When we have material which has orthotropic material, which is a cubic symmetric or a square symmetric, that means we have same stiffness in horizontal and vertical. Then it's also quite okay when we interpolate the orthotropic base structure, because it's fine when we have a single.
Yeah, but then I would say that this depends on the parameterization.
Yes.
Because what you just referred to is when we have one parameter to uniformly scale the cell or vary the volume fraction, then we can apply this type of interpolation.
Yeah, but this is also the point where we go to the grayness, because we started from a representation of the cell as a structure. And you also talk about a structure, but the idea is, well, we have the structure, we can homogenize the structure to get the material coefficients, but it's cheaper and quicker when we approximate the intermediate material tensor by just scaling the tensor with a simple power law. When we do now topology optimization, we only have this power law. We do not really think about what is the structure behind. We just see the gray material, the more or less gray material. And what we showed here is actually where this gray material comes, because this gray material had originally a really physical interpretation, because we thought about this periodic structure, this microcell structure.
So this is our interactive topology optimization tool, which was developed by some former PhD students at our chair, and we often use it to demonstrate basic concepts of topology optimization. Here we have the standard cantilever two-dimensional case where we have some support on the left side, and then the right side we apply a force. So we have a force which is applied here and goes in the negative y direction. Here we see an optimization results for a linear interpolation scheme. In this specific case, the intermediate densities that we see here can be interpreted as the height of a variable thickness sheet. But in general, these intermediate values are not physical, and which means that they are not directly interpretable.
Can I shortly interrupt?
Yes.
With various signal sheet, because this is what I like from the idea of this topology optimization. So what we have in this Kikuchi paper is here the variable signal sheet. That means we scale the intermediate material linearly. When we scale the tensor with 0, we have no height. When we scale it with a high value, we have high material, and intermediate material means, well, half weight, half stiffness.
But the height also indicates the thickness of the sheet, doesn't it?
Exactly.
Yeah.
So this is the same variable, but it only works in 2D, and it only works when we want to interpret our design by varying the height. So in the original variable signal sheet problem, there is, for example, no reason to limit the maximum height by 1. We can have it arbitrary high generally. And when we talk about grayness and materials scaling, we have our original material, and we scale it with variables from 0, which means we have no material or void. And when we scale it with 1, we have the underlying core material. It's very, very close to what we have with the variable signal sheet, but slightly different.
I would directly jump to another paper from Martin Benzo and Ole Sigmund, where the authors discuss different material interpolation schemes for topology optimization. And at one part, they talk about isotropic microstructures. Here you see 2 plots where also these power law curves for a penalty of 3 and 2 are plotted. And that's the part where also the Hauschen-Strickman bounds come into play, because for solid void composites, they tell us where the lower and especially where the upper bounds for realistic isotropic microstructures lie. So if you would draw this linear material interpolation into this plot, we clearly see that this linear material interpolation is unphysical and has no meaningful representation in realistic applications.
When we have topology optimization and we have the gray material, it's a question what it is. Here, we know we can interpret intermediate material by microstructures. And then we have for this lattice structure with a certain density, material density, we have a representation of the material properties. We can find it by homogenization, or quicker by scaling it with a simple, for example, power law or Hauschen-Strickman law or ramp law or whatever. But the question is on how realistic is it in the end? Okay, back to what we have as standard topology optimizations. That means we need some kind of regularization, and we need some kind of intermediate penalization. That means now the optimizer doesn't really want to have intermediate material. It actually has only solid material on the outside or no material at the inside. We have this only as a consequence of the density filter.
So we have now a penalization of material interpolation, which is more physical than the linear one. And now we have the intermediate densities at the boundaries, also a bit in between now. Would you say it makes sense to put the microstructures that we have seen in the paper of Benzo and Sigmund at the boundaries of this structure?
Not at all.
Well, the question is also from a physical point of view, if it really makes sense to put some porous structure around a solid structure.
Yeah.
If you think with respect to stiffness.
That's nonsense. This doesn't help the optimizer never wanted it. It's enforced by regularization only.
So the gray boundaries are just an artifact of regularization. If you would choose a different regularization technique, could be possible that you can avoid these gray boundaries.
Yeah, and we can approximate it by just making the filter smaller, smaller, and smaller. Let's see if it works like this. So it's the number here, it's this filter radius times edge element size. And we see this is one of the smallest possible filters we can have. We have a much better compliance. And the gray is almost completely gone.
How would you now interpret such a structure, or how would you give it to manufacturing? What do you do with the borders or the red elements now?
Well, I would
you just cut them away?
To answer the question, clearly I would cut it away. I would make it a smooth material and no material interface.
But if you look at the middle of your design now, if you would just cut the red elements away, you would have some unstable connection at some point.
Yes. Yeah. And for this, one needs, we should have a feature size, like a heavy side filter.
What was your impression about this first TopOpt-Talk?
Much more difficult than I expected. And I'm curious on what we get when we cut it out. I did not come to what I wanted to talk.
I think it's difficult to fit such a academic content into a fixed time frame.
Yeah, and I find it difficult to do it without formulas, but I find it also a little bit difficult to do it with formulas, because when we have formulas, maybe we shall explain everything, but one needs to find a balance. A little bit more formulas shall be good, but what's the conclusion?
The conclusion is that grayness in general doesn't have a direct physical interpretation. It's a tool or an artifact of relaxation such that we can perform topology optimization, gradient-based one. This is my conclusion.
My conclusion is that it's all in the old papers. And I find it very natural that one doesn't read the old papers. I always was in the beginning afraid that I said, oh, it's an old paper. Probably I cannot even read the notation. Notation changed a little bit. But it's worse in the end. And we are not done with grayness.
No.
I think we can at least have 2 more podcasts just about grayness, up to we come to a point where we wanted to start, which is what we want, or what we talked about in WCMO.
I think grayness is there's a lot to discuss on, and I also have the feeling or impression that there's a lot of misunderstanding.
Probably because the concept seems so simple, and it is in some sense. It's easy to get it misunderstood, I would say.
It's easy to apply it without understanding it. I think maybe that's why there's so much misunderstanding, because people don't think about it.
And I have my lecture about Introduction to Structural Optimization, which is SIMP. And now, after some years repeating this lecture, I introduce it as now in the first lecture, I say this is the intermediate materials, this is grayness. And in the end of the lecture, we will talk about this topic again, and hopefully then you understand it when we have homogenization and so on.